Hi there, this is Callan Bentley. Welcome back for another pre-lab video. This week in lab we're taking a look at earthquakes, and we're going to use earthquakes to actually take a look deep inside the earth where no person can ever go. Have you ever experienced an earthquake? They are pretty dramatic events, and after you've been shaken you might wonder where all that shaking came from. Well, the deal is this. When there's a fracture in the earth and stresses build up along that fracture, and those stresses are greater than the friction that's holding the fracture in place, then the blocks of rock on either side of the fracture slip relative to one another. This makes the fracture a fault. The spot where the fault slips is known as the hypocenter. Oftentimes in the news after a big earthquake, you'll hear a different term, and that is epicenter. Epicenter refers to the spot on Earth's surface directly above the hypocenter. Sometimes as the fault makes it all the way to Earth's surface, you'll get a fracture that actually shows up at the surface, and that's called a scarp. Now, seismic energy is transmitted through Earth's interior, and it comes in several flavors. Those are illustrated here in this diagram from your lab manual. You will notice that there are three types of seismic waves, or earthquake waves. The first of those is called a P wave. P waves are compressional waves. They're the very fastest of the different kinds of seismic waves. So they will always show up first, no matter how far away from the earthquake you are. Second is the S waves. S waves are also body waves, meaning that they travel through Earth's interior, just like P waves, but they're a little bit slower, so they show up second. And then lastly, there are the surface waves. Surface waves are the slowest of the earthquake waves, and they only travel along the surface. So they do not travel through Earth's interior. Let's take a look at these three different seismographs here. The first one basically shows that we have 2 minutes between when the earthquake happened and when the P wave arrived. Whereas with the second seismograph, you can see 3 minutes have elapsed between the earthquake and the arrival of the P wave. And down here with seismograph 3, we can see that there's a full 5 minutes that pass between those two events. You'll also notice that the S waves take longer to arrive the further away you are. In the first example, it takes another 3 minutes for the S waves to arrive. In the second example, it takes another 4 minutes. And here in the third example, we don't even know because the S waves haven't yet arrived. So that time, that proportion between the arrival of the P wave and the arrival of the S wave, that is really important for figuring out how far away the earthquake is. So this week in lab, you're going to be using the difference in arrival times between the first P wave and the first S wave to figure out how far away the earthquake is from three different locations. So the way this works is you look at the seismograph, you figure out when the P wave arrived, you figure out when the S wave arrived, and you do the math. So say the difference is 3 minutes between them. You use the scale, the vertical scale on this graph to measure out a distance that is 3 minutes tall, if you want to think of it that way. So a little scrap of paper, mark the distance from 0 to 3, and then slide that over between the S wave curve and the P wave curve till you find the spot where it fits exactly, perfectly snug, not too big, not too small. That amount of time correlates to a specific distance away from the earthquake's epicenter, and that's about 900 miles in the case of this 3-minute travel time. On the other hand, the further away you are, the more distance there's going to be between the P wave and the S wave. So let's consider an example where the difference in our arrival times is 6 minutes. So if we slide that over, we're going to see that it fits much more over toward the right side of the graph, and that's going to correlate to a distance of about 2,800 miles away from the earthquake's epicenter. If you aren't going to use miles and you'd rather use the metric system, you have that option as well. The distance in kilometers is shown up at the top of the graph. So here's what you can do with that distance information. You can use it to draw a circle, and the radius of that circle is going to correspond to the distance that you calculated. For instance, in this diagram, you can see the city of Montreal has a S minus P time that correlates to a distance of 8,400 kilometers away from the earthquake. So every point along this red circle is exactly 8,400 kilometers away from Montreal. And so the seismologist would know that the earthquake occurred somewhere along that line, along that circle. So then you got to go and match that up with data from 2 other seismographic stations. So let's take a look at Paris. It's 6,700 kilometers away from Paris. So Paris says the earthquake is going to be somewhere along this orange line. That orange line crosses our red line in this spot here and then in another spot on the other side of the world. And a third seismographic station, in this case Sao Paulo, Brazil, has a different distance to the earthquake. And in that case, that third circle intersects the other 2 circles at one location and one location only. That location is the epicenter of the earthquake. So the way this is going to work for you in lab is after you calculate what the difference is in the arrival time of the P waves and the S waves, you're going to translate that into a distance away from the earthquake's epicenter, and then you're going to plot that information on a map that looks like this. So for instance, let's say we had one seismographic station in Central America, and it gave us a radius that looked something like this. So we go ahead and draw a circle to match. Then we get another seismographic station maybe in northern South America, and that has another radius for another circle. You'll notice that that intersects our circle in 2 locations, so we know that the epicenter must be at one of those 2, and we just need a third seismograph to tell us which one it is. So let's pretend we go and consult one from the northeastern part of the United States, and that intersects our previous 2 circles in one spot and one spot only. In this case, in the western part of the island of Hispaniola in the country of Haiti. So that's where our epicenter would be for this particular earthquake. One thing you'll notice about this diagram that I didn't talk about is that all of the body waves, the P waves and the S waves, are traveling through the mantle only. And I didn't look at the complications that result when they go down to the core mantle boundary. There they can refract, which means they change the orientation that they're moving at, or they can bounce off the core mantle boundary. There are additional complications with Earth's inner layers. The actual pattern that seismic waves take on can be more complicated than just a simple curving path. It can look something like you see in this diagram here. These different paths tell us something about Earth's interior. They tell us that we live on a layered planet, and that our planet has a mantle, it has a crust that's on top of the mantle, and it has a core beneath the mantle, and that core has several components, a liquid outer core and a solid inner core. Those different components are illustrated here. You can see that the mantle basically goes down to a depth of about 2,900 kilometers, and then the outer core goes from there down to 5,150, and the middle of the planet's about 6,371 kilometers down. So we've got the inner core here, the outer core, which is liquid, and the mantle. If you zoom in on the mantle, you will find that there is a weak portion of the mantle called the asthenosphere, and then we have the upper mantle joined to the crust. That makes the lithosphere above that. This is another graph that you'll be using this week in lab to answer some questions. Basically, it's a similar cutaway of the planet where you can see over here on the left side of the picture a typical cross-section through Earth's interior. And then the right side of the diagram is a graph. And that graph shows the velocity of P waves and the velocity of S waves as they travel through the different levels in Earth's interior. You can see here on these graphs that there are several big breaks. There's a big break, for instance, at the inner core, outer core boundary, a big break at the bottom of the mantle where it meets the outer core. And then you can see some other interesting little complications higher up in the mantle. Each tell us something about the quality of the rocks that we find at that level, the conditions that they're under, and how they're responding to those conditions. So you're going to answer some interpretive questions based on those. Well, good luck sussing out how these earthquakes can help us see into Earth's interior. I hope you enjoy the privileged view that you get this week in lab. Good luck.